Welcome to Math 119, Chapter 8.4, where we talk about trig equations. So an equation that contains trig functions is called a trig equation. So much like finding your inverse function, we must evaluate where the trig function is equal to a particular value. So such as in example 1, it says solve a basic trig equation, find all solutions. So if we have 3 minus 6 cosine of x is equal to 0, right, what would you do typically if and all this is we're going to replace your trig function with just a variable. What would you do with the variable x if we were asked to solve? Well, first thing that you might do would be to subtract the 3. And then what? Well, and then you would say we would divide by the negative 6. So then we'd say, well, x is equal to 1/2. So same idea here. Instead of dealing with an x, do all of those things that you had previously done, but with your trig function. So subtract your 3, negative 6 cosine of x is equal to negative 3. Divide everything by a negative 6. And here you'll see you have cosine of x is equal to and this is a positive 1/2. Now take what we know from chapter 7.6. What can we do to apply to this cosine function? What theta, what x do we need in order to get out a 1/2? Well, if we take our unit circle here, and if we were to look closely at your unit circle, cosine being your x value, well, pinpoint where all of the locations where cosine is a positive 1/2. Well, that would be here at pi over 3. And again here at 5 pi over 3. So at these two locations, you can see where your cosine has a positive 1/2. So that means your x, your theta, is pi over 3. And again, at 5 pi over 3. Now let's say we wanted to get all of your solutions because they didn't say, actually they did say find all solutions. So we found 2 of many, right? So meaning that we have to add what to this in order to get coterminal angles if we were to circulate around your unit circle. We then add 2 pi n. What we did to one, we would do to the other, 2 pi n over here. So this will give us all of the locations or all of the coterminal angles to pi over 3. And again, at 5 pi over 3. Now let's have you guys try the next one, B. Well, again, treat this as you would kind of like we had an x squared minus 1 is equal to 2. Well, what would you do here? Well, we would have added the 1. So we're going to do that over here as well. So now you have tangent squared of x is equal to 1. Over on the other side, you have x squared, not 1, is equal to 3. So now here we would say x is equal to plus or minus the square root of 3. The plus or minus because, right, you made your square root sign similar to right here. So we just took the square root of both sides. So let's do that for your tangent as well. We would get the plus or minus root 3. So tangent is equal to plus or minus the square root of 3, which again, from your previous chapter, right, your previous section 7.6, your inverse, we said that in order to get this root 3 out, we're looking at pi over 3, where again, on your unit circle, if we were to just plot the unit circle really quickly, notice that I'm not really going over the unit circle much here because at this point in time, we were tested on your knowledge about the unit circle. So that knowledge should be gained here. So at pi over 3, you'll notice that you have the coordinate 1/2 and root 3 over 2. Tangent being y over x, we have the square root of 3 over 2 all over 1/2. So keep, change, flip. Sorry, times 2 over 1. So you're left with root 3. Now this is where a positive root 3 is going to occur. So at pi over 3, that'll happen. Where else will a positive occur? Well, a positive will also occur at 4 pi over 3 because they are both negative. If we change them to be both negative, they cancel each other out and give the positive half. So a pi over 3 and 4 pi over 3, these will provide both positive values. So then what about the negative counterpart? Because you do have a negative here. So the negative root 3, and this is the positive root 3. Well, that would provide us with 2 pi over 3. And again, add 5 pi over 3. Because this is where your coordinate, we have negative 1/2 and a root 3 over 2. So root 3 over 2 all over negative 1/2. Same idea here. We've just now have one that is negative. The negative doesn't cancel. It remains behind. Same thing down here. So that was at 2 pi over 3. And again at 5 pi over 3. So you have multiple solutions here for x. So x is at pi over 3. X is also at 4 pi over 3. X is also at 5 pi over 3. And again, at, 2 pi over 3. Now here, right, we could also add 2 pi n to all of these. And it gets a little redundant. So another way to write your response is to take the positive one, the first positive one, and notice how far away is it from the other positive one. Well, it's about a pi. Actually, it's exactly a pi. So instead of adding 2 pi n, what you can also do, and maybe I just rewrite it over here, the other response is that we're looking at the first take on your positive, and instead of adding 2 pi n, we're just going to add pi n. So if you went this way, that could just n as being 1, or the clockwise version, it's a -1. Or if you wanted to rotate more, right, it's just going to signify whatever n is. If you didn't want to rotate at all, it could be 0, right? But it's going to flip-flop between this positive one and this positive one. Now try it again, but with your negative. Well, the first negative counterpart we actually had was here. So maybe I switch those two values. All I have to do is really just erase their numerator. 2 and 5. So we're going to take 2 pi over 3 and add pi n. So this is a response that's a little bit better, the one that you're seeing probably most often. I'll still accept this one on any sort of exam, but just know that there is another format to providing this answer. Now let's have you try it one more time with example 2. However, this one only differs slightly because instead of finding all of your solutions, it wants to find your solutions between 0 and 2 pi. So within one full rotation. So all we're doing is we're just getting rid of this 2 pi n tacked on at the end. So see if you can pause the video and try these out yourself. So here we have 2 sine theta plus 1. So again, treating your sine theta as just a variable. First, we would subtract your 1. And then we'd divide by 1, or divide by 2. So now on your unit circle, we're looking for where sine is equal to a -1/2. Well, your sine value being your y value, we'll be looking at a -1/2. So this being over here at 7 pi over 6. And once more at 11 pi over 6. So your theta is equal to 7 pi over 6. and theta is equal to 11 pi over 6. Again, you can always use your reference angle from what we picked up from previous sections. We know that pi over 6 will give us the 1/2 value of it. And now in order for us to be negative, we have to be found in the third and fourth quadrant. Now notice that these are in fact your answers. You don't need to add anything on it because it's found within one full rotation of the circle. Let's try it again one more time. So here we can go ahead and subtract a negative root 2. We can then go ahead and divide everything by a negative 2. So we have cosine of x is equal to root 2 over 2. So we know we should be working with pi's over 4. And even better, on your coordinate, right, we want a positive. So that would be both in the first and the fourth quadrant. So in your unit circle, if I were to grab that one more time over here, unit circle. So we're looking at pi over 4. And again, 7 pi over 4 will give us that positive counterpart. So x here is equal to pi over 4. And again at 7 pi over 4. And those are two angles found within that first revolution. So example 1 and 2 are essentially the same exact question. One is just asking for all solutions, and one is just asking for just the solutions found within the first rotation. So that is just kind of from a linear perspective. Notice that you just add and subtract things across from the equal sign. However, right, from what we've done previously, we talked about quadratics next. So factoring is one of the most useful techniques for solving equations, including your trig equations. The idea is to move all terms to one side and factor, then use what we talked about from previous sections called the zero product property. So see if you can pause the video and try out this particular equation. So go ahead and factor. Notice that everything is already on one side. That's great. If they weren't, we have to pull everything over because we have a square here. So let's go ahead and factor. So when you factor, hopefully you got something like 2x minus 1 and x minus 3 is equal to 0. Now, because factoring was way back in chapter 1, we're not going to be talking about slowly breaking it down here because that is a skill that we should already have picked up. So this being the zero product property, we have everything being factored. Now we get to set this both equal to 0. So x is equal to 3 and x is equal to 1/2, right? And then we would just say, okay, this is our response and we're done. So if we were to move on to example 2 with something like this with your trig function, let's say kind of like we did with the very beginning examples in example 1, where if I took your cosines away and I just replaced them with a variable, we would get something like this. Have we seen something like this before? Well, yeah, that was the one we just covered, right? We said, well, we really got 2x minus 1, x minus 3 is equal to 0. We also even got x to be 1/2 and x to be 3. So for us, we didn't just have an x though. Our response, we have 2 cosine of x minus 1 and cosine of x minus 3 is equal to 0. We can set these equal to 0 and solve. So cosine of x is equal to 1/2 and cosine of x is equal to 3. Now take a look closely at some of these values. Again, trying to use our idea of your inverse trig. We just don't have nearly as many restrictions because it's not an inverse cosine that we're looking for. So for our values, right, where is cosine equal to 1/2? Well, I believe we had that question earlier, right? On your unit circle here, where is cosine equal to 1/2? Well, we talked about that being your x value. That's at pi over 3. And again, at 5 pi over 3. So x is equal to pi over 3. And x is equal to 5 pi over 3. Again, this x being find the angle. Now, where is cosine equal to 3? Well, on your unit circle, right, think about your domain and your range, right? Well, we can, our range, right, we can only hover between +1, let me see if I can highlight, +1 here and -1. So that means if we're looking at 3, 3 is clearly out of bounds. This does not exist. So this is not going to be a valid response. It is a no, or it's an undefined solution. So that goes for your sine function as well and your cosine function, right? It is not capable of achieving something that is outside of our bounds here. Now, this would be good if it asks for just some of your, or just two solutions. If it wanted all solutions, so if all solutions, what would we add to these two? We'd say, okay, plus 2n pi and plus 2 pi n, or 2 pi n, 2n pi, doesn't matter. So let's have you try it again, one more time with B. Now, if this is hard to start to pick up, how would you factor this normally, right? What if we had x squared minus x is equal to x plus 3? Well, because there's an x squared, let's move everything to one side. So let's add, or sorry, let's subtract this x because it's already positive, so it makes more sense to subtract. We'd get x squared minus 2x minus 3 is equal to 0. And if we were to keep going, we could say, okay, well, this is really x minus 3 and x plus 1 is equal to 0. However, we don't really just have an x, we have a sine of x minus 3 and another sine of x plus 1. We can set these equal to 0. So sine of x is minus 3 is equal to 0. So sine of x is equal to 3. And sine of x plus 1 is equal to 0. So sine of x is equal to -1. So where is sine equal to 3? Well, on your unit circle, we said that is out of bounds. So this one is another does not exist. Where is sine equal to -1? Well, that is all the way down here, 0, -1. So this is at 3 pi over 2. So x is equal to 3 pi over 2. And if I said, hey, can you find all of your solutions? Just add 2 pi n. Now, if you haven't paused the video, try it on C. Now, C, if you're, again, having a hard time getting started, are sine and cosine the exact same? No, so they would be different variables. Let's say cosine is x, sine is y. Minus 2, it's a cosine, so let's say that's x. What would you do with factoring here? Well, you would factor out a GCF. X minus 2 is equal to 0. And again, we don't have this in reality. We have a cosine of x and a sine of x, or of theta, minus 2 is equal to 0. I'll just swap these with theta. Keep it consistent. So let's go ahead and solve. We have cosine of theta is equal to 0. Sine of theta minus 2 is equal to 0. So we're looking at where cosine is equal to 0. So again, on your unit circle, where cosine is equal to 0, That's all the way right here at pi over 2. And again at 3 pi over 2. So when theta is equal to pi over 2, and again at 3 pi over 2. You could find all solutions by just adding 2 and pi to both, or even better, just because they are a full pi away from each other, you could also just say pi over 2 plus pi n because they are fully separated by a pi. So in either direction, by going just a positive and negative, n can give you just a back and forth motion. Now, where is sine equal to 2? Well, that does not exist. So that is finding your, or working with trig functions. So evaluating trig equations, kind of from a linear approach, and again, from your quadratic approach.